All right, so let's start. So today we would like to finish the proof of the convexity theorem, and we'll spend most of the time talking about Morse theory. Probably some of you already know it very well. Some of you maybe kind of hear some of the details for the first time. In any event, it's probably part of it will be hand waving, but part of it will be more like honest explanations. So so let's look a little bit at the Morse theorem. So the context here is as follows. So we start with a compact connected manifold M, and we consider a smooth function f on M. And well, we consider the critical set of this function, which are points on M where the differential of f vanishes. So suppose we choose the point in this critical set. So then there are several things that happen there. First of all, if we take any vector field on M and we differentiate our function f using this vector field and compute this derivative at M, then it is equal to 0. That's just because the alternative writing for it is the computation of the differential at M on the value of the vector field at M. Right? So since this guy is already 0, then all these derivatives vanish at 0. The alternative, by the way, the alternative writing for this expression, is it visible? This maybe I should take some other color. So the alternative writing is the Lie derivative of f computed at M. So that's one thing that happens. So and the other thing, as you may know, there is a Hessian bilinear form which is defined bilinear form, so it is symmetric. So maybe if we write it in local coordinates, that's something that you know very well from the calculus classes. So if we take this Hessian form computed on two vectors. So then what we get that's how it looks like. Maybe in somewhat more invariant notation, it would look as follows. Suppose that U and V are tangent vectors at M, and let's say capital U and capital V are vector fields, such that their values at M are exactly equal to small u and small v. So then what we can do, we can define this Hessian as LU, LV applied to F, and all of it computed at M. Now, well, from this definition, it's not quite obvious that it's symmetric, right? So why is it symmetric? So in fact, if you take a difference, right? Let's exchange the roles of U and V. So then, because of the properties of Lie derivatives, you will get L U bracket V F computed at M. But then we know that this is 0 by this property, right? So any Lie derivative of F at a critical point is 0. Right? So that's 0. But actually, I said it's symmetric, but even to start with, it's not completely clear it's well defined, right? What does it mean, well defined? You see, I chose some vector fields with given values at that point, but maybe I choose some other vector fields, right, with the same value. Would it only depend on this value? So maybe it depends on something else. For that, maybe we can do the following. So what did I want to say? Right. For instance, we can now U of M is 0, right? So assume that one of the vector fields vanishes at that point. So then LU, LVF of M, so this will be what? This will be D LVF of M paired with U of M, and this is 0, right? So if the vector field vanishes at that point, you get 0, at least for the first entry. For the second entry, it's less obvious, right? But on the other hand, what happens, we just proved that it's symmetric, right? So for the second entry, that's going to be the same. And so the same applies to V. Okay. So now a couple of definitions. So F, a smooth function of M, is a Morse function if crit M is a discrete set. In our case, since M is compact, this implies it's a finite set. And so this bilinear form is non-degenerate. Is non-degenerate at all critical points. Yeah, non-degeneracy is defined in the usual way, similar to symplectic forms. So we introduce the kernel as all vectors n all vectors with the property that the bilinear form vanishes for all v in TMM. And we say it's non-degenerate if the kernel is 0. So that's a good definition. But in the moment maps theory, we actually need a somewhat more elaborate definition. So this is a kind of version, or one can say an upgrade of the definition of a Morse function. So f is a Morse-Bott function. So here what we want is as follows. Well, and you will see it kind of already similar to things that we saw before in the context of group actions. So now we want a critical set to be a disjoint union of submanifolds. And so that's one thing. And the other thing, we want so connected, let's say. So the connected components of the critical set are smooth submanifolds. And let's choose a point on one of those critical submanifolds. So we want the kernel of this Hessian bilinear form to be exactly the tangent space to this critical component. So that's roughly what we want. So maybe we give some easy examples, and then we would perhaps use those examples in a discussion. So one example is not a true example because I want to give you an expression for some function in the local chart. So I take M to be Rn. So this is not a compact manifold, but I'm thinking of some local chart. So, and I would like to split my coordinates in 3 groups. So I will split the set 1n into a disjoint union of I, j, and k. So there are 3 subsets. And I'm choosing my function near the origin, which is just 1/2 sum over I in I xi square minus 1/2 sum j in j xj square. And as you see, there is no dependence on the coordinates in the last set. Right. Now, what's the critical set of F? It's clear if you take a differential, right? So the differential will be some xi dxi minus xj dxj. So for differential to vanish, you need the coordinates xi and xj vanish. Right? So this means that this will be some kind of subspace passing through the origin. So that's this crit F. Of course, as I say, we don't need to think about it globally. We can, but we can always think that that's what locally happens on some neighborhood of the origin. So that's this critical set. Now, what about HF of M? So let me maybe a little bit prematurely think of it as a matrix. So I'm just taking the matrix of second derivatives, right? So the matrix that we wrote. And so what will be this matrix? Right? The second derivatives with respect to xi's are ones, right? So they will be ones. So then with respect to xj's, they are minus ones. And then finally, there is no xk dependence. So that corresponds to I. That corresponds to some set j. And this is the subset k, right? So it is. So these are the corresponding blocks. And now we do see that the kernel of HF of M, so that's exactly the tangent space. Let's say, let me choose origin as the point of the critical set. And this is TMF, where F is this subspace. So that's an example of how Morse-Bott functions look locally. So that's a model. Now let me draw some more pictures. So let me take M to be a sphere S2 that I imagine is a round sphere in R3. I don't know how round is my sphere, and I consider a function which is just one of the coordinates. Now, what would you say? How is this function? Where is the critical set of this z coordinate? So I restrict the z coordinate to sphere. Where is its critical set now? So the critical set where the differential vanishes. So I have this yellow chalk prepared to draw it. Right. So that's, of course, that needs to be checked. But so these are the two. So these actually, in this case, the critical set is discrete. So there is the north pole and the south pole. Now, in this configuration, what about the Hessian? What do you think? Is the Hessian non-degenerate, right? So for that, of course, is already a question that needs to be in some way studied. But if you write, for instance, if near the south pole or the north pole, we choose the local coordinates x, y, the other two coordinates, then of course we know that z will be plus or minus, depending on which pole we choose, 1 minus x squared plus y squared. Right? So the question is whether the second derivative is non-degenerate. Of course, like we know, we can write it as a Taylor series. So how is it? This would be plus or minus 1, probably here 1/2, right? X squared plus y squared plus so on. And from here, we do see that actually it does look like, so the Taylor expansion, the second term of the Taylor expansion, it does look like what we want. So it's going to be non-degenerate. So do you agree? Is it a good reasoning? Right. So this is the is a Morse function. In fact, one can easily imagine that if we deform the sphere a little bit, if we like flatten it near the, right? If I try to deform it and flatten near the poles, so then I can probably easily make the second derivatives vanish. Right? So then it's not going to be a Morse function. So now it is a Morse function, but flatten it a little bit such that the second derivative disappear. Maybe you get only fourth derivatives. So then it will not be a Morse function. Maybe two more examples, preparing for some future considerations. Somewhat less formally, let me take a two torus, again embedded in R3, so something like this, and I take a projection, so F will be projection, let's say, on the vertical axis. Well, what about the critical points here? So imagine, right, that's a donut. What are the critical points of this projection? So certainly this guy and that guy and similarly here. So there will be four functions. So here, if it's a kind of solid torus, it's relatively easy with similar arguments to convince oneself this would be a Morse function. And let me give one more example. Imagine I try to deform this embedding of the torus, and I arrive at something like this. So, right, so basically I don't touch so much the upper part, but in the lower part I kind of start pulling, and I create two minima here. So, up there the critical points won't change, and here it's not going to change. But now, of course, something changed here, right? So how would it look like, right? There will be, in all probability, critical points down there, and a new critical point will be created here. So, right, it becomes less and less formal, our pictures, but one can imagine such a thing. So this is again, this is a kind of torus, right? But deformed a little bit, and I'm still projecting to this line. All right. So now let's develop our theory a little bit. And let's choose G a Riemannian metric on M. So then one can do the following. Suppose that M is a critical point. So then one can rewrite the bilinear form, the symmetric bilinear form defined by the Hessian as the bilinear form defined by the metric. And here you would get some linear operator, right? So now we have two bilinear forms. G is a non-degenerate bilinear form, so any other bilinear form can be written in such a way where HM is an endomorphism of TMM. And it's going to be symmetric. Since this is symmetric, so this is going to be symmetric with respect to this bilinear form. Symmetric operator. Well, as any symmetric operator, it's going to have real eigenvalues. And we can now split TMM into a sum of TM0M plus TM positive M plus Tm negative M, where that's the eigenspace. So that's for H, that's for the, with respect to the operator HM. So that's the eigenspace for lambda equal to 0. That's the direct sum of eigenspaces for all positive lambdas, and that's eigenspaces for negative lambdas. In fact, if our function is Morse-Bott, we already know what this guy is, right? So that's the kernel of the operator HM, and as a consequence, that's the kernel of the bilinear form. So this guy is the kernel of HM, which is the same as the kernel of the bilinear form. And if the function is Morse-Bott, that's the tangent space to the critical submanifold. Now we are getting like two more interesting subspaces, one of them corresponding to positive eigenvalues, another one corresponding to negative eigenvalues. So now some more players in this game, even though somehow I don't want to erase anything. Okay, probably I would have to redraw the pictures later. So once we have a metric, we can define the gradient vector field. Let me denote it. How do I denote it? I denote it in this way. So the gradient vector field for the function f, well, historically we define it as minus df. So we want the metric to send this vector field to minus df. Perhaps it's good to recall, remember, some time ago we already wrote similar equations for the symplectic form, right? So the definition of Hamiltonian vector fields, it was exactly like that, only instead of G, there was the two form omega, and on the right-hand side, there was a different sign. So this is a Hamiltonian vector field. Right, so our manifold is compact. So UF integrates to a flow that is a family of diffeomorphisms of M. And now the Morse theory is the following interesting game. So we define sets W plus I and W minus I. So W plus I, these are points of M, such that the limit of phi t of M when t goes to plus infinity belongs to Fi. So you see here already, of course, kind of here my hand waving starts a little bit because in principle you need to show, right? So we take a point, we take a trajectory under the gradient flow. So here I am already assuming that it converges somewhere, right? So what we're saying now, it converges somewhere and it converges to some critical point. So the critical point has to belong to one of Fi's, and so I'm looking now at those M's which would converge under the gradient flow to a given Fi. And here this would be a similar definition. But now we're going to run the flow in the opposite direction. So the facts are that these are they're actually submanifolds of M. So those stable and unstable sets. So this is called the stable submanifold, and this is called unstable submanifold. So let me perhaps state some facts about them, some easy facts about them, and then we'll look at examples. Facts. So one fact is as follows. So we get a decomposition of M into a disjoint union of stable submanifolds, or alternatively a decomposition of M into a disjoint union of unstable submanifolds. Here, of course, kind of implicitly, I'm saying that all the trajectories converge to critical points, right? And that's how these decompositions are obtained. So there are no trajectories where something weird would happen. For instance, no trajectories which would not converge somewhere. So as I said, so these are actually submanifolds, and we actually know their dimensions. We'll see now in examples roughly why it happens in this way. So the dimension of the stable submanifolds, so they are obtained as dimensions of Fi plus the dimension of Cm m plus for m in Fi, and there is a special name for this dimension. So this is equal to this is denoted Ni plus, and the dimension of Wi minus. That's the dimension of Fi plus dimension of Cm minus m, and this is Ni minus. Right. And then, well, if this is true, then obviously the codimension of Wi plus is Ni minus, and codimension of Wi minus is Ni plus. So let's look at our simplest example. So our simplest example was this model, local model on Rn, right? So the function was 1/2 sum I xi square minus 1/2 sum j xj square. Now let me say that I choose the metric which is simply the constant metric. So the sum of dxs's for all coordinates. So this means that in particular this bilinear form Gm, this will be the standard Euclidean scalar product on Rn. Now what about the gradient flow? How would the gradient flow look like? Right, it should be a vector field. How does it look like? Should we first, so let me recall, df is a sum over I in I xi dxi minus sum over j in j xj dxj. So now we need to convert it into a vector field, right, by applying the metric. So could you tell me how it's going to look like? So here, so will be still a sum over I, right? Here will be sum over j. So here xi d over dxi, right? Here xj d over dxj, right? So that's what the metric does. Now what about the signs? Yeah, here will be a minus sign. Here will be the plus sign. Okay. Now, how would those stable and unstable manifolds look like? So, right. Suppose so this was K, right? So that's where nothing actually happened. So this would be I, and this would be J, let's say, right? So the critical submanifold is this one. That's our F. That's our F. Now So what's the stable submanifold? So we need to see from where the gradient trajectory would fall on this line. So where is it? So what is in this case, what is our W plus? Right, so we need kind of, so we run the gradient flow. So gradient flow is very simple, right? So that's our gradient flow. So we run this gradient flow, and actually, like, that's a vector field. But what does it do, the gradient flow? Right, so here we have, like, just let's imagine that it's just three-dimensional as I draw it. So there is this k coordinate, there actually nothing happens. There is the I coordinates, that's the kind of positive one, and the j coordinate, that's the negative one. How does the flow look like? So the gradient flow. Yeah, that was a good. Right, so it is, right, it is contracting along the I coordinate, and it is like expanding along the j coordinate. You can actually write it down, right? It's exponential decay along the i's coordinate and exponential growth along the j's coordinate. That everybody follows me, or should I write it explicitly? Everybody follows me? Okay, good. So this means that this W plus, this will be the IK plane, right? So that's where the trajectories, so here the trajectories are falling on this K line. What will be W minus? W minus means that we run the time in the opposite direction, right? So we would change here the signs. So now, by analogy, this should be the JK plane, right? So that's the JK plane. So these are, so if you run time in the correct direction, there everything is escaping. But if you reverse the direction of the time as we should in the definition, then that's how locally it looks like. By the way, maybe like one test question. Here I said that M should be union of like positive or whatever those stable submanifolds and the union of unstable submanifolds. But here it doesn't look like that, right? I have my critical set. It's here. And here is this plane in this free space, which is a stable submanifold, and another plane, which is an unstable submanifold. So why is that? So this doesn't seem to hold, this fact. Yeah, that's because this is a kind of local model. So there should be somewhere other places where, for instance, this escaping flow, it should end somewhere if we are on a compact manifold, of course. So let's finish this hour with by looking maybe at least one more example. So what about a compact manifold example? So let's say I have this round sphere. So that's my function. I said there were two critical points, so the south pole and the north pole. So let's talk about those W pluses. What are stable submanifolds? So we have a gradient flow. The gradient flow is, as you can imagine, right? So the gradient flow runs in this way along the meridians of the sphere, right? Now, what will be the stable submanifold of the north pole and the stable submanifold of the south pole? So what falls on the North Pole if t goes to infinity? So only the North Pole itself, right? And all the rest going to fall on the South Pole. So that's S2. Of course, if you look at unstable submanifolds, their roles will exchange, right? So there, the South Pole will be its own unstable submanifold. So what about? So what about this guy? So here there is A, B, C, A, B, C, D. So let's try to make a drawing only for stable submanifolds. So W plus of A. So that's again A, right? So nothing can possibly fall into it. What about B? What falls on B? Well, a circle probably without one point, right? So there will be this part, and then on the other side there will be that part, right? There will be these two things falling here. Now, what about C? Right. So that's again a similar thing, right? So that's the stable. So that was the stable submanifold for B. The stable submanifold for C, and well, for D. It's just the rest of it, right? So that's the stable submanifold for D. By the way, I said they are submanifolds. Indeed, so this is an open interval. This is an open interval. Now, what's the stable submanifold for D? How can you imagine it? Right? It's two-dimensional. So what you do, you first cut your torus there, so you get a cylinder, and then you cut the torus, your cylinder again. So this is a product of two open intervals. So this stable submanifold for D. All right. So let's have a break, and after the break, we still continue just a little bit with Morse theory, maybe for 5 more minutes before we return to moment maps and finish the proof of the convexity theorem. With the Morse theorem, and I would like to give you one more fact, which is the key for the convexity considerations. So assume that the negative ni's, those negative indices, they're all different for 1. So then there is a unique I such that F minimum on Fi. So maybe, like, before discussing why is it true, so recall that we have this Hm. It has 0 eigenvalues, which correspond to the tangent space to the connected component of the critical set. It has positive eigenvalues here, and it has negative eigenvalues there. So what does it mean for a critical point to be a local minimum, right? Again, like as in the first year calculus, so M, say in Fi, which is a part of the critical set, is a oops, what's going on? Local minimum if and only if the corresponding ni minus is 0, right? So you shouldn't have those negative directions because that would explicitly contradict to the local minimum condition. So what we're saying now, so if ni minuses cannot be 1, so then there is only one fi with ni minus equal to 0. So there, the points of it are local minima, but they're also global minima because there are no other local minima, right? So that's what we're saying. So why is it true? So let's consider M prime to be M without the union of the stable manifolds which correspond to ni minuses non-equal to 0. So these are stable manifolds which correspond to FIs where you do have negative directions, right? So now we know their codimensions, right? Their codimensions are equal to ni's. Is equal to ni minus. And, well, sorry, yeah, not equal to 0. So it's not equal to 0, but it also cannot be equal to 1 now, right, with this assumption. So if it's not 0 and not 1, then it is at least 2, right? So we excluded the ones which correspond to 0. Those which have 1, they do not exist. So this is at least 2. So this means that we take away from connected manifold M some number of submanifolds which codimension at least 2. Then it remains connected. Because if you have a path from somewhere to somewhere, then you can always make it generically not intersect those things of codimension at least 2 that you are taking away. So M prime, so because of this, M prime is connected. Okay. So M prime is connected. Now, what is this M prime? M prime is a union of all the other stable manifolds, right? So we excluded ni minus different from 0. So this is a union of stable manifolds with ni minus now equal to 0, right? Well, but now this guy is connected, and this is a disjoint union of these guys. So this should be only one of them.
Sorry, I don't see why, like either WI open or...
Yeah.
Okay, cool.
Yeah, they're open. Sure. Is it true what I'm saying? Yeah, for those ones, yes, they're open. Maybe to a little bit better understand how it works, let me give you a counterexample. So recall that we had this picture for the deformed torus, right? Now this one does have two local minima, right? So how the stable manifolds look like here? So the stable manifold of this guy is just itself. The stable manifold of that guy, that's as before. That's this. So the stable manifold of this one is this. And finally, the stable manifold of this one is this, right? So now the stable manifolds of these two guys, right? They are disjoint, so that these are the two halves of the remaining torus. That's what flows there, and that's what flows there. So why we were able to separate them? That's because we had this n minus equal to 1 things, right? So they were able to separate our manifold into pieces, right? So it was connected, but now we kind of successfully built a wall between these two, like this one and then that one, and that's because of this n minus equal to 1 points, critical points. So that's how it works. If it were already codimension 2, then we would not have been able to split it, and we would have to have just one local minimum, which is also a global minimum. Here there are many points with so all these points, they have n minus equal to 1. Right. Perhaps here a couple of remarks. Of course, if ni plus is not equal to 1, then there is a unique local maximum, and it's also a global maximum. Something more complicated. If both ni plus and ni minus are not equal to 1, so then fibers of the Morse-Bott function are connected. For OX. So this is more complicated, and this is used in the other strategy, in the ATIA strategy of the proof of the convexity theorem. Here again, you see that for the torus, even if we don't have those unpleasant local minima, so here we see that the fibers are sometimes disconnected, right? So that's the fiber over this point. But again, we have there n minuses and n pluses equal to 1 for these two. So for these two critical points n minus is equal to n plus is equal to 1, which is, as we see, always very bad, and we have those disconnected fibers. Right. So with this, let's leave Morse theorem, at least for a while, and let's return to Hamiltonian geometry. Proposition. So let's consider the compact connected Hamiltonian T-space. So let's choose an element, let's say non-zero, in the Lie algebra of the torus. Yeah, I would like to make, yeah, I'll add one more assumption, but so then mu psi C infinity of m is a Morse-Bott function. So the components of the moment map, the projections of the moment map, so they are actually Morse-Bott functions. So why is it true? So let's discuss the critical point set of those components. What is it? So these are points on M such that d mu psi of M is equal to 0. Now, of course, we can rewrite it as iota of psi M omega, right? So that's by the moment map equation equal to 0, since omega is non-degenerate. So this is the same as psi m of m equal to 0, right? So so these are points on M where psi m of m equal to 0. And as we discussed already several times, that's the same as fixed points m t psi, where t psi is the closure of the subgroup spanned by psi. Right? So that's the critical point set. In particular, of course, we know that since this is the fixed point set for a compact subgroup, this means that this critical point set is a union of smooth submanifolds. So that's because of this interpretation. Well, now let me recall the following. We know that if we choose M in this critical mu psi, so this is equal to M t psi. So then, recall we have this decomposition, right? TMM would split into the tangent space to the corresponding submanifold Fi plus this will be a direct sum of R2s, and on each of those R2 isomorphic to C, this T psi action will be as follows. So Zi will be mapped by what? So if we choose here this exponential of S psi acting, so what will it be? So this will be Zi exponential, and here, what should I say? Right. This will be something like this. I, S, N, I, N, what? Maybe I is not a good letter. K, and K psi, where these are weights. Of T psi, right? So that's one of those expressions for the action that we wrote. So there will be this action and those nk psi here is not equal to 0, right? Because if it were equal to 0, then the action on this particular z would have been trivial, and this R2 it would have been here, right? So that's how it looks like. Now let's think about it in the following way. So we know that we have a Hamiltonian action of T on M. But then, of course, we also have a Hamiltonian action of T psi on M. So T psi is a subtorus of T. So we have T. It contains T psi. It acts on M omega. And this action is Hamiltonian. So what's the moment map? Right, we have T psi, the Lie algebra, injects into T. So this means that we have a projection from T star to T psi star. And the moment map, let me call it mu tilde, is this projection composed with mu. So that's the map from M to T psi star. Right. So now, last time we spent like kind of the whole class writing up some kind of normal forms for a moment map near a critical point. And a critical point of a moment map is a fixed point for the action. Now you see this T psi acts. It fixes M. So there is this moment map mu tilde. So what's the normal form of the moment map mu tilde near the fixed point M. So a normal form near M. So remember, we looked at those normal forms, and there are like those spectator coordinates along the critical coordinates on Fi, and then there are those z coordinates, actually the z coordinates from here, right? And the expression for the normal form was something like this, unless I'm mistaken. So this is sum over k zk squared times nk, right? So there was a that was basically, you remember last time it was a somewhat painful consideration, but the beginning was maybe not so bad, and so that was right. So that was the outcome. So the moment map looks near a critical point. It's very, very easy. It's sum of those like positive things. The absolute value squared of zk's just times the weights. So let me use it to compute a normal form for mu psi. So I compute the normal form for mu psi, but actually, because of this projection, I can simply replace mu by mu tilde, because psi is in t psi. So to evaluate a linear form on it, it's sufficient to project it to t psi star, right? That's just by definition of this projection. So mu psi is equal to mu tilde psi and is equal to 1/2 sum over k zk squared, and here nk psi. So near a critical point in some well-adapted coordinates, the function mu psi looks like sum over squares of the corresponding zk's, which means squares of just the Euclidean distance on the corresponding R2s times some coefficients. And these coefficients, right, they are all non-zero. Because if they were equal to 0, then this the corresponding copy of R2, it would have been in this part, right? So then some of them are positive, some of them are negative, and this would decide for you what is the positive subspace and what is the negative subspace. However, the important outcome that we see from here, it all comes in copies of R2. So you can never have any n plus or n minus being odd, right? Because it's always zk squared times whatever. There are some number of zk's with positive coefficients and some number of zk's with negative coefficients. But like you never get like any one real direction which will be positive or negative. They all come in pairs. So this normal form tells you that ni pluses and ni minuses are all even. But if this is the case, then this unpleasant case of ni equal to ni minus equal to 1 or ni plus equal to 1, it's just not there. Okay, before saying that, so you see we kind of even computed the normal form near a critical point, and this normal form is just exactly as the normal form I showed you in the beginning, right? This Rn example. So it is like that. So this means that the Hessian will be non-degenerate, and that this is indeed a Morse-Bott function. So this, so even before before saying that, we see that mu psi is Morse-Bott because we just explicitly know how it looks like near critical point. And then on top of it, and ni plus minuses are un or I. In particular, recall, this means that every such function, it has its local minimum is necessarily a global minimum, right? So that's what we saw before. Is a global minimum. Right? Well, let's try to finish the convexity proof. So let me recall what we saw last time. Well, so we have our manifold M. It is sent to T star by the moment map. And here we would like to consider a neighborhood of some point, right? So this point is mapped to its image, mu of M. So, and we explained how the image of this small neighborhood looks like there, right? So it looks like the following thing. So you're taking mu of M, you add into it Cm, so it's a polyhedral cone, and you intersect it with some neighborhood of mu of M. Right? So Cm consists of sums with positive coefficients of some integral vectors. And generically, the situation looks as follows. So you have your point mu of M, and then maybe there are some flat directions, and in some other direction there is this polyhedral cone. So that's the polyhedral cone Cm that is shifted to the point mu of M, and we intersected with some W. So the image of U. The image of U looks like this, right? So it's an intersection of some neighborhood of mu of M with a polyhedral cone, possibly with some flat directions, right? So that's how it looks like. So that's a local. So that's a local. Local normal form. Yeah, from this somehow we now want to, so that's a polyhedral cone. So from this somehow we now want to want to conclude on the global structure of the image, right? So we know how it looks locally. Now we want to glue our knowledge together. And so first of all, let me introduce. So we have a polyhedral cone. So this is sitting inside C star. So let me introduce a dual cone in T. So this will be elements psi in T such that the duality as psi is greater or equal to 0 for all x in Cm. So the duality of cones is reciprocal. So it's easy to see that Cm is now actually equal to the set of x's in T star such that S psi greater or equal to 0 for all xi's in Sm. So we can. So now we kind of constructed this dual cone, but we can use it also to get back our cone Cm. Right. So now we want to prove the following claim. But actually, I said locally it looks like an intersection, but actually all of mu of m is inside this cone. So mu of m cannot, like for instance here, I cannot have points of mu of m, right? So this is already a global statement. Whatever my manifold is huge, whatever huge manifold, whatever it is, it will all be somewhere within this cone. Okay. So why is it like that? Right. So let's consider psi in the dual cone Sm. Right, so then I would like to show that M is a local minimum of the function mu psi. So I think this is more or less obvious, right? So local minimum, what does it mean? This means that on this neighborhood U, the minimum value of mu psi should be at M, right? Now, so locally, we know that the image looks like that. So now we take a duality with psi. So the duality of psi on all the vectors of Cm is positive, right? But now the vectors of Cm, that's exactly the difference. So let's say M prime is in U near M. So then mu of M prime minus mu of M is in Cm, right? And this means that mu of m prime minus mu of m psi is greater or equal to 0, right? That's a proof of it, right? So then this means mu psi of m prime greater or equal than mu psi of m. Right? So if I choose any psi in Sm, then mu psi has a local minimum at m. So that's more or less by this local normal form and the definition of Sm. But then this means that m is a global minimum of mu psi, right? So that's what we discussed. That's actually, because of this small moment, that's we were turning all this machinery of the Morse theorem. That's because we needed, at some point we need to make some step from local to global. That's our step from local to global. So m is a global minimum of mu psi. Well, what does it mean that m is a global minimum of mu psi? So this means that for any m prime in M, mu of m prime minus, mu of m prime psi greater or equal than mu of m psi, and this means, of course, mu of m prime minus mu of m psi is greater or equal to 0. But this is a statement for any psi in Sm, right? So for any psi in Sm, mu of m prime minus mu of m psi greater or equal to 0. And that's also for any m prime in M. So this means that mu of m prime minus mu of m is NCM by this statement. Right? So this means that all the image of M, whatever it is there inside this CM. This was a crucial step, but still there is a little bit of things to do. So we actually showed that mu of m. We showed that mu of m is contained in the product, in the intersection of these sets. Right? So we take one such set, and then here we take another such set, and then here we take the third one, and somewhere here there is an intersection. And within this intersection somewhere there is mu of m. At the moment that's the picture. So one claim is that this right-hand side is actually a convex polytope. So this is a convex polytope, and that's essentially because of the following. Remember, so there is this local normal form. So that's our point mu of m. So then, if you take those local normal forms for the neighboring points, then the corresponding cones will be equal or bigger than the one for mu of m. So for all the neighboring points, you will get for the other points. This means that actually you can take an open cover of your M by the neighborhoods U, and from each neighborhood it's sufficient to take one of those polyhedral sets. So this actually means that here you can take open cover, so union of ui's is equal to m, and then of course we can choose a finite, since it's compact, we can choose a finite cover, and in each of the covering sets it's sufficient to choose one of those sets. So this is actually a finite intersection of polyhedral sets, so which means it's a polyhedral set. So replace by union mi. Right. So, and finally, we say mu of m is equal to this set. So why is that? Imagine if that's not the case. So we have our polyhedral set. So that's the right-hand side, and mu of m is compact, and there is a point here. There is a point x which is outside mu of m. So mu of m is somewhere there. So then let's choose the closest, or one of the closest points to x on mu of m. Of mu of m. And consider this segment. So the segment connecting x to mu of m. So here, so this closest point, say y. Y is equal to mu of m for some point of the manifold, right? Because it's in the image. So this means that here there is again a local normal form as before, right? And the points of this segment, with the exception of y, they do not belong to this local normal form, to this cone. So here we have a neighborhood, and part of this segment does not belong to this normal form. But we know that mu of m is entirely inside this normal form, and so this means in particular this point does not belong to the corresponding cone. But this is a contradiction, because we said it was in the intersection of everything, so it has to belong there. So this is impossible. So it's impossible to have a point outside this set, because it would not belong to the local normal form for the closest point. Right? Maybe I write it explicitly. So y is equal to mu of m, and we see that this segment is not, so has no intersection with mu of m plus cm. right? So this means that X is not is mu of m plus Cm, and this is a contradiction. Because it was supposed to be in all the in the intersection of all the sets for all m's. Well, it's probably a good point. It's probably a good point to stop. Let's kind of we still discuss some things about convexity in the beginning of the next class, but with a little bit of hand waving, this completes the proof of the convexity theorem. As I mentioned, that's one of the strategies of the proof. So we worked out those local normal forms, and now using the Morse theory, we glued them together. Now, the alternative proof that I mentioned, that I did not present here, it's a little bit in the exercise session, which will take place now. So there, you first show that the fibers of the moment map are connected. And that's where you're using the Morse theory. So you cannot do it without Morse theory. So you use Morse theory to show that the fibers are connected, and then you use the fact that fibers are connected to prove convexity. So that's somehow a different route. But you see that you have to use the same pieces of the puzzle to get the result. That's probably, I think, the last big theorem that we'll have during the next two classes is the localization theorem, and to some extent, I think it's easier. That's probably the most complicated fact we prove in the class. All right, well, thank you. Let's have a break.